Hi, my name is Jamie Church, and today we're going to be talking about mobility shift assays and footprint assays with general transcription factors. This video was made for MCDB 427 Molecular Biology at the University of Michigan. Enjoy! First, let's just start with a general overview of transcription in prokaryotes versus eukaryotes. Now in prokaryotes, upstream of the +1 site, we have the -10 site and -35 sites. This is where RNA polymerases can come and bind to. With euks, we have a little more going on. First off, they have three different RNA polymerases. They have RNA polymerase I, which makes the ribosomal RNAs, RNA polymerase II, which makes the mRNAs, and RNA polymerase III, which makes small RNAs. For this video, we're just going to be focusing in on RNA polymerase II, but know that the methods we're going to be talking about are very applicable and could have been applied to RNA polymerase I or III. Another distinction between prokaryotes and eukaryotes are the promoter elements. In prokaryotes, upstream of the +1 site, we have the -10 and -35 sites. In eukaryotes, upstream of the +1 site, we have the initiator sequence, we have the tadapox, we have the BRE, and we have both upstreams and downstream promoter elements. Euks, yeah, they got it going on. What these promoter elements are is they're places for general transcription factors to bind to. These general transcription factors are going to recruit and orient RNA polymerase in the proper position so we can get correct gene transcription. Now, how we label these general transcription factors is TF for transcription factor, followed by a number. This number tells you which RNA polymerase 1, 2, or 3, for example, that this general transcription factor is associated. Followed by a letter. Now this letter distinguishes it from all other general transcription factors that might be associated with a particular RNA polymerase. Now to save time, I'm going to omit the TF2, but just know that in this video I'm only referring to general transcription factors that interact with RNA polymerase II. To further save time, I'm not going to constantly say RNA polymerase II, I'm just going to refer to it as POL. So these transcription factors, they bind in a certain order. First, we're going to have D come and bind. It may or may not be associated with A at this point. Then we're going to have B come and bind. Then we're going to have RNA polymerase come in, but it's going to come in with F. Remember this, it always comes in with F. Then we're going to have E bind, and then H, bam, we are ready to roll. Now this is cool. Yes, you know it is. But someone had to figure this out. So that's why we're talking about mobility shift assays and footprint assays today. Let's look at the first one. So let's just start with mobility shift assays. Now, this was the original image from the paper, but it is like hard to read. So I'm going to rework it so it's easy for everyone to understand what's going on. Now remember, with electrophoresis, small things, they travel through the gel faster, so they're going to appear lower down on the gel. Now let's start with lane 1 because starting with other lanes would be, well, ridiculous. Now in lane 1, what they did is they add transcription factor D and A. And you can see that these things bound because they weighed that bad boy down, causing it to appear higher up on the gel because it's heavier. This makes sense. Now in lane 2, they have the exact same thing, but they also add B this time. And you can see that B has bound because the blot now appears higher on the gel, so it's heavier. What we can't say is that B is bound to the DNA or has it bound to transcription factors. We just don't know. Now in lane 3, it's the exact same thing as lane 2, but you add F, and the blot doesn't change the size. I mean, it's at the same position, so we can safely assume that F is not binding to other transcription factors or to the DNA. So for lanes 4 through 7, what they did is they kept all the transcription factors at a constant, and they increased the concentration of RNA polymerase II. What they found is they got the original two bands again, that is the DA band and the DAB band, but they also started getting two new bands. That would be the DB pol F band and the DAB pol F band. Now these are kind of hard to see the distinction, so here it is. So look at the band intensities for the top two bands. Those are the pol bands. Now as we increase pol, they get darker. This means there's more pol binding. Now at this point, we don't know if transcription factor F is actually doing anything. Maybe it is, maybe it's not. So that's really what lanes 8 through 12 address. They keep all the transcription factors and RNA polymerase at a constant, and they just decrease F until we get to lane 12, where there is no F. And if you look at the band intensities for where you see pol binding, it goes down, and when we have no F, there is no band, meaning there was no pol binding. So at this point, what we know is that transcription factor F and pol are required for them to bind. If you don't have one, it's not going to happen. But what they want to figure out is the order of binding for all the general transcription factors. So that's what the next lanes are going to address. Now in lane 13, we have all the general transcription factors plus pol. The only thing we're going to omit is transcription factor D. And what happens? Nothing. What do I mean by that? Is there are no bands. None of the other transcription factors bind when we omit D. Now in lane 14, what they did is they omitted B this time. Now we do get a band, it's the DA band, but we get no bands with pol. So pol cannot bind without transcription factor B. Now in lane 15, what they did is they omitted transcription factor A. Now we do get a band. It's very high up, so we know pol is there, but it's a little lower than the standard pol. And that makes sense because if we omitted transcription factor A, there's one less transcription factor. It should run a little faster. Now lane 16, it has everything. It's really like a control to compare all the other bands to. It's nice. So what are some conclusions that we can draw? Well, first, we can say that D binds first with or without A, then comes B, and then third comes RNA polymerase with F. Remember, it comes in with F. I've said this enough times. Remember. Okay, let's move on to the second mobility gel. Now again, I'm going to rework this because it's like impossible to read. Now in the first lane, they have D, B, pol 2, and F. We're omitting A because he didn't do anything for us last time. Now in lane 2, what they do is they add E. Now it shifts up a bit. It's hard to see, but the original authors, they say it did, so let's trust them. Now in lane 3, what they do is they add E and H, and this time we get a noticeable shift. So both E and H are binding. So in lane 4, what they did is they omitted pol, and we get the DB band, and this makes sense because these things don't require polymerase for binding. The interesting bit is we don't get a band higher than that, so we know E and H aren't binding. They must bind after pol and F. In lane 5, what they did was they omitted F, and again we get the DB band. In lane 6, they omitted B, and we don't see anything because there's no B there. The only thing that would be binding is D. For this gel to run with an E and H, you have to run it a really long time. So most likely, the D band just kind of ran off the gel. In lane 7, they omit D, and we just really get nothing again. Now one problem I have with this gel is it really doesn't address the order of binding for E and H, but spoilers, it goes E, then H. Now as bloody cool as all this is, there's one major flaw to the mobility shift essay. It tells us that things are binding, but not how they're binding. And what I mean by that is we don't know if things are binding to the DNA or if these transcription factors are binding on top of each other, sort of like a totem pole. Because they want to know how things are binding, they do a footprint assay. Now again, remember, small things that travel through the gel faster, so they're towards the bottom. Now the two strands on the left are template strands. The two strands on the right are non-template strands. So remember with the footprint assay, what we have is we have radio-labeled DNA, and then we add a small amount of DNase. The DNase is going to randomly cut, so we're going to get a ton of bands. The only place that we wouldn't have bands on the gel is where our protein is binding to the DNA. It's going to be protected, so we're going to have this blank region in the gel. So they actually use two different footprinting methods for this assay. They use DNase 1, which has enzymatic activity, and they use this copper complex, which has chemical nuclease activity. It's common in science to use two different methods. It's a way of double checking. Now in lane 1, all they have is radio-labeled DNA and the DNases. You can see we just get a ton of bands. Nothing was protected. There are no blank regions because nothing is binding to the DNA. In lane 2, what they did is they added transcription factor D, and you can see in the DNases there is a small blank region, so transcription factor D is binding to the DNA. Now in lane 3, what they did is they added transcription factor D and A, and this blank region increases, so you know both transcription factors are binding to the DNA. So for lane 4, what they did is they had transcription factors D, A, and B. Now it would be logical to conclude that B is not binding the DNA because this blank region isn't increasing in size, but spoilers, I actually know for this strand of DNA, there just wasn't a promoter region for B to bind to. Now this is the actual area that the transcription factors are binding to. I omitted it earlier in your slides. I thought it cleaned them up a lot. And you can see that A and D, they're binding to the Tata box region. And for your information, D actually binds the Tata box. Who knew? Well, now you do. Now in the second footprint gel, what they want to look at is they want to look at RNA polymerase binding. Now in lane 1, what we have is we have the radio-labeled DNA, and we have a small amount of DNA, so we get a bunch of bands. In lane 2, they have transcription factors D, A, and B, and we get a blank region because these things bind to DNA. In lane 3, they also add RNA polymerase and transcription factor F, and we get a huge blank region. Why? Because RNA polymerase is now binding to the DNA as well. Now just look at the difference in size. The DAB region is from the -42 all the way to -17, but just RNA polymerase region is from the -17 all the way to the +17. I know what you're thinking. Whoa, mind blown? Mine too. So what conclusions can we draw from these experiments? So many. From the mobility shift assays, we can get the order of binding. We know first it's going to be D with or without A. Second, we're going to have B bind. Third, we're going to have RNA polymerase come in, but it's going to come in with F. And fourth, we're going to have E and H bind. Now from this mobility shift assays, we can't determine the order, but we just know that it's going to actually be E then H binding. Now from the footprinting assays, what we can determine is how things are binding. We know that D and A are going to bind to the DNA. From this assay, we would conclude that B actually binds on top of them. That's not true. We actually know it binds to the BRE region. After that, we know RNA polymerase is going to come in and it's going to bind in front of D and it's going to cover a huge swath. Now I hope this was all very helpful and you learned something about footprint assays and mobility shift assays. And as always, go blue.